Well, hello class, I'm Brandon Lashbrook here with my research for you. Today we're going to be looking at upper level synoptic flow patterns for cases of tropical cyclone rapid intensification in the Gulf of Mexico. So let's go ahead and get right into it. Now, intensity forecasts are a vital part, a big part of the story for any landfall and tropical system that affects land and communities. Now, rapid intensification in of itself is defined as an increase of a tropical cyclone's 1-minute average maximum sustained winds by at least 30 knots within a 24-hour period. That is the National Hurricane Center's definition. Now, periods of RI, or rapid intensification, within a storm's lifespan can make forecasts a little bit challenging. Take Hurricane Otis, for example, a couple of years back, and are of course of high importance for any coastal communities where some of that time to prepare may be limited for a strengthening system. For example, here Hurricane Laura back in 2020. Now, understanding potential synoptic scale patterns in the upper levels of the atmosphere that may influence and impact the tropical storm environment is of importance for the forecaster to help increase warning lead times if we can see some upper level patterns that may potentially favor periods of RI. So therefore, an analysis of an upper level synoptic pattern, sort of a climatology of a pattern that may favor that RI period within the Gulf of Mexico, is of interest, as we see again a lot of troughs and ridges coming across the continental U.S. that may play a role in in some of these storms that potentially rapidly intensify. So look at some of the literature review out there. Tropical cyclone track forecasts in of themselves have seen large improvements over the past few decades, as of Demaria and et al. But when examining the intensities, also there has been improvements with the intensity, but the forecast scale for rapid intensification is still relatively on the lower side. Again, take for example Hurricane Otis a few years back. The intensity of a tropical cyclone is found to be influenced by the synoptic scale environment present, as well as the dynamics and the thermodynamics of the environment. So it's not just the upper level air patterns and the geopotential height distributions that are present. There are a lot of other things that go into play into the intensity of a tropical cyclone, such as the troughs and ridges in the upper levels. Wind shear is a big player as well. The ocean conditions, the oceanic heat content, and the sea surface temperatures act as that fuel for tropical systems to intensify, as well as relative humidity and maybe also smaller storm scale processes that are in play within the core of a storm. Now, the upper level height distributions may aid or limit potentially the degree of intensification of a tropical cyclone. One study by Bracken and Bozart examined the upper level environment over the western Atlantic basin, and their composite results show that for tropical cyclone Genesis, we see 200 millibar hectopascal trough to the west relative to the disturbance, and a ridge off to the east. Similarly, Miller at 1958 also examined the upper levels, but only with a general strengthening of tropical cyclones, not just Genesis or rapid intensification in the Atlantic. His results indicated a trough to the northwest was in the climatology, a high to the east, and an anticyclone off to the southwest. Again, all of these positions relative to the storm center. And the results from these studies suggest that positions of the upper level features found can promote divergent flow aloft, which is crucial in talking about conservation of mass, with mass evacuating from the center of the storm, rising up and aiding into the storm's outflow. The mechanisms that trigger rapid intensification continue to be a subject of ongoing research, where most research kind of suggests the RI of a tropical cyclone is a complex system and evolution of its intensity, which is kind of facilitated by environmental factors as well as those inner core processes as the eye wall forms and kind of works to tighten up the core. Sometimes we see a rapid intensification potentially follow after that. Upper level flow is just one piece of the puzzle that may potentially promote or favor rapid intensification. So upper level trough interaction may increase the divergence or potentially work to increase wind shear, which is detrimental to tropical cyclone strengthening. One study noted that trough interaction occurs in a minority of RI cases in the Atlantic, thus suggesting that most RI cases occur without this specific upper level trough-induced divergence pattern, which is interesting. We'll get into some of the results in a bit. So, research question that I proposed was the idea of trough interactions for RI within the Gulf of Mexico is of particular interest to examine potential climatology in the upper level synoptic pattern in RI cases against non-RI cases, so storms that may strengthen but just not at that rapid intensification criteria. Now, the question is there an upper level disturbance or upper level flow pattern rather, or height distribution pattern around the tropical cyclone that is favored for tropical cyclone RI cases compared to non-RI cases? So the hypothesis is an upper level trough will be present to the northeast of a tropical cyclone with a ridge or anticyclone positioned to the east in RI cases, and is there any statistical significance against these non-RI cases? Data that was used was the best fit track and intensity data collected from the National Hurricane Center HURRDAT2 database, as well as the NOAA Historical Hurricane Tracks archive online. And this included 6 hourly observations for location, maximum winds, minimum central pressure, plus extra entries for any landfalls or any max intensities as well that were noted. Reanalysis data, gridded reanalysis data, was also used from the AR5 data set based on single levels and pressure levels as well, obtained from the Copernicus Climate Change Service and the climate data stored there. Variables analyzed from that data set included the mu and the v components of the wind, geopotential height, sea surface temperatures, relative humidity, relative vorticity, divergence, wind shear, and surface pressure as well. Some of the limitations of the data is that the gridded AR5 reanalysis data can suffer from the lack of true observational data that is inputted into the model, especially over water, where again some of that model data or some of the observational data rather is lacking in terms of upper air balloons. So we do get the hurricane hunters flying over some of these storms, but elsewhere the data is lacking in terms of an observational sense. And so one pitfall with some of these gridded data, especially in tropical systems where we have such high wind speeds and such low pressure, sometimes it can underestimate the wind speeds themselves and the mean surface sea level pressure as well in some of these local extreme events such as in hurricanes. Now, the research here less focused on the actual speeds and the pressure values, as we're looking more so in the upper levels and more so in the geopotential heights around some of these tropical cyclones. So methodology, we're looking at some of the case selections. A 20-year period was analyzed from 2001 through 2020 to keep it short enough that data analysis is manageable, but long enough to get a reasonable sense of a couple of decades. Now, the Gulf of Mexico is defined as the body of water between a couple of these longitude and latitudinal coordinates, and I'll show you the map for that. Here are the cases of rapid intensification that were identified between these 2001 and 2020. On the map there you see the gray dashed line, that's the borders or the boundary indicated for the Gulf of Mexico. Here are the tracks of all the storms that did undergo an RI period. Again, that's 30 knots or greater within 24-hour increase within the area of interest. Cases were selected as RI begins in the area of interest. So this did exclude, for example, Hurricane Rita, which began to rapidly intensify to the east of the Gulf of Mexico and to continue to do so into the basin, looking more specifically here at storms that began an RI period within the Gulf of Mexico. So again, that does omit storms that began the RI period outside of the Gulf and then moved into the Gulf. So you see in the red dots there, those are the 6 hourly positions from the HURRDAT database of when the storm was rapidly intensifying, and so there's no real clear-cut trend of where in the basin that most of these systems happen. It's kind of all over the Gulf of Mexico kind of waters there. There's no real high density in some of these cases in one area or another in the Gulf. Now, the cases where the storms did not have an RI period, a few of those were selected as well to compare. Equal spatial extent across the Gulf for similar environmental conditions were looked at, and they were at least tropical storm strength and either in an intensifying stage but below that RI threshold or in a steady intensity. So some of the methodology we're looking at geopotential height and wind direction and degrees values. They were extracted and in a gridded fashion around the storm of interest from the AR5 data. So looking at some points around the center of the storm, 1 degree, 3 degrees, and 5 degrees to the north, south, east, and west of the system, and also in diagonal too, so northwest, northeast, southeast, and southwest by using Pythagorean theorem. So again, that's about 3 degrees to the west and 3 degrees to the north will get you that second measure there. Then data was averaged over the sample at the time frames that were analyzed were at the start of the RI period for each case. Now this data was visualized and analyzed within GRADS, ArcGIS Pro, and R software as well. So a couple examples of cases. Here is Hurricane Zeta in 2020. You can see in the upper level pattern flow a nice trough to the northwest of the storm, southwesterly flow with down the upper levels to the east, a nice anticyclone ridge there, some higher heights, and southerly flow just to the east of the storm in the upper levels. Hurricane Lorenzo, another RI case. However, the upper level patterns were very different as the storm was in the Bay of Campeche. So to the north, very well to the north, you have some lower heights there. To the east, actually, you do have a little bit of a trough setting up with the northerly flow in the upper levels, and then to the southwest and more so west, a little bit of an anticyclone there. So very different upper air pattern compared to the previous storm, Zeta. One storm that did not meet the threshold for RI that was looked at as well was Hurricane Hermine in 2016. To the sea to the north, a slight trough, almost zonal flow though. To the north, to the east, a little bit of an anticyclone in place and a little bit of higher heights too. So some of these were looked at and compared to those RI cases. So as we averaged out the geopotential height distributions over the RI cases to the left and the non-RI cases to the right, you can see on the RI cases to the left some higher heights relative to each other. To the northeast of the center, to the northwest, the heights are beginning to drop the more northwest you go. A similar story to the right on the non-RI cases, those heights still begin to drop to the northwest, but instead of increasing to the northeast, they increase to the southeast as well. Now the arrows here represents the average wind direction in the upper levels. Again, that's 200 millibars. And you see a similar story overall. We do have overall, you see where the outflow flow is with a kind of northerly, rather southerly to southwesterly flow to the northeast of the center, southwesterly flow to the northeast, and also to the northwest. And a little bit different story to the southeast of the center. We have southwesterly flow in non-RI cases, but more so easterly flow in the RI cases as well. So some of these statistical analysis that was used were the geopotential height differences calculated between the outermost point, so that's that 5-degree point, and the innermost point, the 1-degree longitude or latitude point close to the center of the storm, in each one of those directions. So northeast, north, northwest, east, again from the center of the storm. Now a chi-square test was used to determine this distribution type, and as of the test, the null hypothesis of a normal distribution could not be rejected, so we're assuming this distribution here of average heights were normally distributed. A one-sided t-test was set up to determine probabilities of negative geopotential height gradient to the northwest that would indicate a trough was more likely present, and a positive geopotential height gradient to the east indicating a likelihood of a ridge based on the sample using the calculated height differences. So the one-sided t-test with a 95% confidence level, that's the probability of 0.05 or less to reject the null in the northwesterly direction. Null hypothesis was height difference in the northwest direction greater than 0 would indicate heights are increasing, but the alternative hypothesis was height difference in the northwest direction decreasing less than 0. Probabilities came out to be less than the probability level of 0.05 within that rejection zone, so we could reject the null, saying that yes, the heights do decrease to the northwesterly direction of the tropical cyclone center. Same test again for the northeasterly direction and to the east of the center of the storm. Although interestingly enough, these results came back as cannot reject the null, so we could not say for sure that the heights do increase to the east of the storm in terms of those average heights that were collected from the sample. Also, more statistical significance was looked at between the geopotential height between the RI and the non-RI cases by looking at the upper and lower 95% confidence level. In the northwesterly direction, we found that the mean of the RI cases was in between the non-RI confidence interval levels indicating that the height difference is not statistically different from the non-RI cases. Differently, as we look to the non-RI mean compared to the RI confidence intervals, which was to the lower end outside of the interval, so it was technically statistically different from the RI cases, however, not in terms of it being ridge or higher or increasing heights compared to lower heights. That would actually indicate that the heights are actually a little bit stronger in the gradient force there in the decreasing direction. Similar story for the northeasterly direction from the center of the storm. The northeasterly height difference is not statistically different from the non-RI cases. And a similar story once again for the non-RI mean height difference compared to the RI confidence intervals. The mean was lower, so more negative, indicating a little bit more of a trophiness to the northwest, or northeast rather, of the storm. In the easterly direction, both RI mean and non-RI mean were not statistically different from the non-RI cases and the RI cases as well, indicating that the overall upper level air pattern is not all that much different compared to the RI cases and the non-RI cases. So looking at some of the conclusions, based on the one-sided t-test with the RI case data, there's higher probability for a trough present with lower geopotential heights to the northwest. However, there is lower probability that higher geopotential heights are found to the east, therefore a ridge. Overall statistical significance was not found in the height distribution from the northwest to the east relative to a tropical cyclone center between RI cases and non-RI cases. Now, while favorable 200 millibar upper level synoptic flow patterns that promote divergence is preferred for a storm intensification, this particular pattern with the trough to the northwest, ridge to the east, is not just exclusive to the RI cases. It can occur as research with cases that do experience RI and cases that do not experience RI. Other factors at play when RI is triggered as well to keep in consideration: ocean conditions, storm scale processes, how the core interacts with itself, maybe the warm core as well, and the upper levels with a mass evacuation indicating pressure falls, all could lead to RI being triggered. Now, further work could include increasing the sample size over a longer period of time, or more storms to look at as well, or we're looking at an average height and divergent features over a longer temporal scale per each storm to maybe get a better picture as we go as a storm kind of evolves over a time frame as well. So here's some of my references that I looked at and some of the data sources too that were used during my research, and I thank you so much for your time.